We're going to talk about acid-base titrations. We've been talking about acid-base reactions, and a titration is a technique which takes advantage of an acid-base reaction. So the idea here is that we've got a substance with a known concentration, and we're going to react that with a substance that has an unknown concentration. The goal is to find that unknown concentration. So we add one solution to the other until we get the reactants in their stoichiometric ratios. And of course, how do you know when you've gotten to that point? That's kind of the tricky part. But that's called the equivalence point. So if you're looking at like HCl and sodium hydroxide, NaOH, the equivalence point will be where you have an equal number of moles of acid and base. Then we can calculate that unknown concentration using stoichiometry. Okay, and people approach the calculations for titration in different ways, and I want you to do stoichiometry, okay, because it always works. And you don't have to learn anything new because we just learned how to do solution stoichiometry, and that's what this is. So with acids and bases, generally the reactants and the products are colorless. So it looks like you're adding water to water, and how do you know when you get to the equivalence point? We use something called an indicator. An indicator is an organic acid that changes color in response to changes in acidity and basicity. So when we see that color change, we know we're at the equivalence point, and then we know that the number of moles of acid equals the number of moles of base, and we can calculate what we've added. So here are illustrations and pictures of what's going on here. Here we have sodium hydroxide in the burette, and this is why we need to learn how to read the burette correctly. And we use the burette to add sodium hydroxide to an acid where we don't know the concentration. So we're going to add sodium hydroxide, and as the sodium hydroxide goes in here, it reacts, the hydroxide from the sodium hydroxide reacts with the hydrogen ions and neutralizes them. When you get to the point where you've neutralized all of the hydrogen ions, that's the equivalence point, and the indicator will change color. This is kind of oversimplifying it, but it's good enough. And what that looks like in reality is something like this. You're adding sodium hydroxide, nothing seems to be happening. When you get closer, you'll start to see little pink swirls. And we're seeing pink there because as the sodium hydroxide comes in, it hasn't mixed thoroughly yet. And so you have a localized concentration of sodium hydroxide, and then when you mix it, it gets neutralized by the acid and the color goes away again. And when you get to the end point, it will turn pink and stay pink. And when we do our first titration, I'll warn you that that's not the color we're looking for. That person maybe went a little too far. But the common indicator that we use is called phenolphthalein. It's kind of a mouthful, and I won't make you spell that. So either nod your head or shake your head. Have you done titrations in lab before? Okay, so a mix. That's expected. So let's do this calculation. The titration of a 20 ml sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of a 0.158 molar KOH solution to reach the equivalence point. What is the concentration of the unknown H2SO4 solution? So this is a titration, but when we're calculating it, it's just solution stoichiometry. So what do we usually have when we do stoichiometry? We usually have a chemical equation, right? They didn't give us one here. We need to write one anyway, because the stoichiometry is very important. Sometimes it's 1-to-1, sometimes it's 1-to-2 or 1-to-3, and it's really important to know that. So the first thing we're going to do is write the chemical equation for this. And we don't need to be super careful and write all the state symbols or anything. We just need to get the formulas. So we've got H2SO4 and we've got KOH. And those are going to react and form something. How do we figure out what they make? The charges are important, and we're going to swap partners, right? Remember the people going to the party in the beaker, right? So we're going to swap partners. So we need to be aware of what the partners are. Well, from the acid, we're going to get H+, and we're going to get SO4 2-. This is ionic. We get K and OH-. So hydrogen came with sulfate. We're going to see how it does with hydroxide, and we'll see what potassium does with sulfate. So we've got H+ and OH-. We have K+ and SO4 2-. What do we get when we put H+ and OH- together? H2O. So that's water. And that will always be one of the products in an acid-base neutralization reaction. And then here we've got K+ and SO4 2-. And so we're going to need 2 potassiums to balance the charge on the sulfate so that this can be a neutral compound. K2SO4. Any questions so far? Now we need to make sure the equation is balanced. Is it? No. What element jumps out as not being balanced?
Potassium.
The potassium. Here it's K, and here's K2. So we can fix that by putting a 2 in front of the KOH. Now there's 2 potassiums on both sides. And, it's usually best to leave the water part for last, hydrogen and oxygen. So let's look at sulfur. This is one where we're swapping partners, and so sulfate stays intact. So there's a sulfate here and there's a sulfate there. So that's okay. Let's look at the hydrogens now. I've got 2 hydrogens here and 2 hydrogens here. That's a total of 4. How many hydrogens on the right side? 2. So I need to multiply that by 2, so I get 4 on each side. And then let's check the oxygens. There's 2 here and there's 2 there. And if you find it confusing to leave these guys out, go ahead and include them. 4 plus 2 is 6, and 2 plus 4 is also 6. So that's our balanced chemical equation. So now let's take the information that was given in the problem, those numbers, right? 22.87 milliliters of 0.158 molar KOH and 20 milliliters of sulfuric acid. And what are they asking for? Concentration of H2SO4. So I'm going to write these volumes under the formulas for those compounds. So the sulfuric acid, there's 20 milliliters, and the potassium hydroxide, there's 22.87 milliliters. And then this is the concentration of the KOH. So 0.158. What does capital M stand for? Moles over liters, molarity. So let's write moles over liters. I actually had a bad dream last night about a student doing crazy things with the units and capital M's. It's like, just had a flashback there. And the question we're trying to answer is, what's the concentration here? Moles per liter. Because when you write capital M, your brain just sees it as a single unit, but it's not. It's moles per liter. Okay, so, our basic path is grams to moles to grams, right? That's the starting point for stoichiometry. And then we're going to look at do we need to switch up the ends? Well, are we given the mass? This is our starting thing, the KOH. We're not given the mass, we're given the volume, right? So that's not mass, it's going to be volume in milliliters. And then we're trying to find moles per liter. Well, that can get to moles. We don't need grams. But how are we going to get to molarity then? We're going to use the equation for molarity. Molarity is equal to the moles divided by the volume in liters. So the moles is what's going to go on top. So this mole is going to be this number. And the volume in liters, where does that come from? The starting volume. We know we had 20 milliliters, and so we're going to need to convert that to liters, but that's not so hard. Okay? So we're doing stoichiometry, volume to moles, and then we're going to take that and divide by the volume of that acid solution and get the molarity. So we've got 22.87 milliliters times, in a line, we're going to moles, need a little more space, moles of KOH. Oh, I should have specified that's KOH. Moles of KOH, and then we're going to moles of sulfuric acid. And then we need units to cancel out. Well, this is a funny looking milliliter, right? The molarity here is moles per liter. So there's a couple of different ways we could solve this issue. We could use millimoles. Another thing we can do is sort of a shortcut unit conversion. The milli here is standing in for times 10 to the minus 3. So instead of writing the milli, I could write what milli stands for, which is times 10 to the minus 3. That's pretty easy, huh? This is not proper scientific notation, but your calculator doesn't care. And I don't care either until you get to the final answer. Then it needs to be correct scientific notation. But here it's just fine. So now I've made that into liters, so then I can have liters down here, and the liters are going to cancel out. And moles down here, moles of KOH are going to cancel out. So moles and liters, that relationship is the molarity of that solution. So 0.158 moles, 0.158 moles per liter. And then here, how do I know what the mole ratio is? From the balanced chemical equation, right? 1 sulfuric acid reacts with 2 potassium hydroxide. So there's 1 mole of sulfuric acid for every 2 moles of potassium hydroxide. And there I've got the unit that I'm wanting. So 22.87 EE minus 3 times 0.158 divided by 2. So this is 0.00180673 moles of sulfuric acid. How many sig figs should that answer have? 3. This one had 4, and that one had 3. So this one should have 3. Leading zeros don't count. So I've got the 1, the 8, and this 0 is my third. So now I can calculate the molarity. The molarity is going to equal the number of moles, and there's only a couple of extra digits, so I'm just going to include all of them, divided by the volume. The volume was 20 milliliters. What does the unit have to be? It has to be liters. So let's use that same trick, and instead of writing milli, let's write what it means. Times 10 to the minus 3. So 0.00180,673 divided by 20 EE minus 3. This should also have 3 sig figs. So we can say it's that many moles per liter, or 0.0903 capital M. Any questions? We're using the definition of molarity to calculate the molarity. We need the moles and we need the volume in liters. The volume will be given in the problem. The moles you're going to calculate using stoichiometry. But it's even an abbreviated stoichiometry. It's only it's only 2 factors instead of 3. Did we have to calculate any molar masses? No, we didn't. That went really fast, right? Because they give you the concentration. So there's a lot less calculating to do. Any questions? Never, never, ever, ever use the dilution equation for a titration. There are people that do that. It's fraught with peril, okay? Because this mole ratio doesn't get in there, right? And so your answer is off. And I know that students like to do that. So in the titration questions on the exam, it's not going to be a 1-to-1 ratio. Because when it's 1-to-1, the dilution equation works just fine. But it's not always 1-to-1, and it definitely won't be on the exam, okay? Because I know students do that, and I don't want you to do that. So that's it.